Thank you, Frank, and first of all, thank you very much to the organizers in Annecy for managing to keep LAPTh 2020 alive and managing to bring us together in this very strange context. It's really a great pleasure to be able to address people directly and not through a computer screen, believe me. So the work I wanted to present here is a work which we did last year in collaboration with Luc Frappin and Eric Ragoussi here, and it is motivated by by a question which started in 1986, actually, when Jean-Michel Maillet first started to derive the classical integrability structure of the complex sine-Gordon model, and where questions were risen regarding what the algebraic structure of this classical integrability exactly was. So let me just now point out what the problem is. Complex sine-Gordon is a 1+1 dimension classically integrable model. It's described by the following Lagrangian, which I wrote here, which is a quite simple object. It's basically a sigma model with a mass term. And the field psi is a complex field with a complex conjugate momentum pi, of course. And the interesting fact is that the complex sine-Gordon is a classically integrable field theory. First of all, it's a weakly classically integrable field theory in the sense that there exists a lax representation of the equations of motion as a zero curvature condition for a certain connection. And that's what's written here with this zero curvature condition. The X component of the connection is the so-called lax matrix, and you see that this is a matrix which is basically function of the field psi and the momentum pi, and it also depends on the derivative of the field psi, which is going to have very strong impact on how the Rmatrix structure behaves. Of course, there is not only the space component of the connection, but the time component of the connection is also relevant, and this is the time component of the connection, which again depends on the field momentum and space derivative of the fields. So there is classical integrability in the weak sense with this lax representation, and there is actually quantum integrability, classical integrability in the strong sense. Because of the zero curvature condition of the connection, you are in a capacity to build quantities out of the lax matrix, out of the X component, which are time conserved. But time conserved is not enough to talk about classical integrability. You need time conservation, and you need Poisson bracket 0 between the time-conserved quantities. You need a full set of time-conserved quantities, Poisson commuting conserved quantities. To obtain this, there is an algebraic object which guarantees the existence of this Poisson, zero Poisson structure. It's the so-called Rmatrix structure. And I'm going to write, you're going to see in the next slide exactly what kind of structure we are talking about. The existence of such a structure was proved by Maillet in 1986, so it guarantees classical integrability in the strong Liouville sense. They previously, actually in 1983, Jean-Michel Maillet and Hector de Vega had looked at the aspects of quantum integrability of complex sine-Gordon, and they had pointed out that there were some issues about the existence of anomalies, and the fact that you had to modify in a rather strong sense, in a rather strong way, the classical conserved quantities which you deduce from the lax matrix in order to get quantum objects. And you really had some issues with associativity and some issues with algebraic structure. And that points out that there is something going on there. And the second point, and the point which is going to draw our attention now, is the fact that this classical Rmatrix structure implies, because the Rmatrix describes the Poisson brackets, as we are going to see, because the Poisson brackets are associative objects, the classical Rmatrix obeys a classical equation. It obeys actually the classical Young-Baxter equation, or some form of a classical Young-Baxter equation. And in the particular case of complex sine-Gordon, a classical Young-Baxter equation was written by Maillet in the same paper in 1986, but it was written in a form which was not completely algebraic. So it was not obvious that this classical Young-Baxter equation could be the classical limit of some quantum algebraic structure. And I'm going to show you why there is this problem. Okay, so what do I mean by Rmatrix structure? Well, because the Lax matrix depends on the field psi and the momentum pi and the derivative of the field psi. Pi and psi, of course, have a delta Poisson bracket. But if you compute the Poisson brackets of the Lax matrix component with themselves, which is the thing that is characterized by the Rmatrix structure in the usual description of classical integrability of a Lax matrix, what you get is a slightly more complicated form than is usually obtained. Slightly more complicated because, first of all, you have non-ultralocal terms with this S and this delta prime terms and with this derivative of the A matrix. A and S are the components of the classical R matrix. A is the antisymmetric component of the Lax matrix, antisymmetric under exchange of the two factors. The R matrix is, of course, something that lives in a tensor product of the two spaces here, and A is the antisymmetric part, and S is the symmetric part. So what you see in the completely algebraic, in the purely algebraic term here, is that what you get is description of Poisson structure by some commutator, except that here and here you have two different matrices, because precisely there is this symmetric component of the R matrix, which implies that you do not have the usual classical R matrix formula that you find, for instance, in the papers by Sklianin, but something more complicated. And you have this non-ultralocality here. Because this R matrix describe a Poisson bracket, and a Poisson bracket is an associative object, and here are the explicit form of the R matrix. So the skew-symmetric part of the R matrix has a very well-known term here. P is the permutation operator. And you have this well-known piece here, which is the simplest classical R matrices. In fact, it's a one-pole rational R matrix, and it's naturally understood as coming from the classical limit of the Youngian structure, of the quantum Youngian R matrix. But you have extra pieces. You have this piece, and you have the S part, the symmetric part of the R matrix, which has also this behavior. And so this means that not only you have an R matrix which is not skew-symmetric, which is not a usual, which is not a very common feature among R matrices. Actually, it is a rather common feature, but it's not so well popular. But in addition, you have dynamical objects, dynamical contributions, dynamical in the sense that they depend on the field themselves. So the R matrix is not skew-symmetric and depends on the field. It is something that had been advocated for years, in fact. Almost the very first paper describing what the classical R matrix was, which is a paper by Semenov-Janchansky in the early 80s, already indicated that an R matrix need not be skew-symmetric and need not be non-dynamical. And if it were non-skew-symmetric and non-dynamical, you had to seriously ask yourself what kind of Young-Baxter equation, a classical Young-Baxter equation, you could get from such R matrices. Turns out that in the case of complex sine-Gordon, well, first of all, in the case of R matrices which depend on the field variables or the dynamical variables, there is a whole class of well-known examples of R matrices which obey algebraic extension of the classical Young-Baxter equation. It's known as the Gervais-Neufelder classical equation, and it has been known for decades. As a matter of fact, the Gervais-Neufelder goes back to issues with Calogero-Moser model, and that goes back to the 1990s approximately. However, it's not the Gervais-Neufelder type that we have here, and the first attempt at putting, trying to understand this in terms of Gervais-Neufelder solutions didn't work. So the question remained, and the question remained on what exactly is the algebraic content of the Yang-Baxter equation. What is the Yang-Baxter equation for this R matrix structure? Put, first of all, the full R matrix is the sum of the antisymmetric and symmetric part. What you get when you write the Jacobi identity for the Poisson brackets expressed in terms of the R matrix is this Yang-Baxter equation, classical Yang-Baxter equation. There is a completely algebraic term which you may notice doesn't have exactly the form that you might be familiar with when you look at the classical Yang-Baxter equation as a limit of the quantum Yang-Baxter equation. That's precisely due to the fact that the R matrix is non-skew symmetric and that you are not allowed to transform this R32 here into minus R23, which would give you the third term of what is very often defined as the classical Yang-Baxter equation. Plus, because of the R matrix dependence on classical fields, dynamical fields, you have an extra contribution when you compute the Jacobi identity, which is the Poisson bracket of the R matrix with the Lax matrix. And this is the extra K object here, which you have to add to the Yang-Baxter equation. And what Maillet had written in 86 was this complete equation with these extra pieces. And there remained to understand what kind of algebraic understanding do we have about these extra pieces. Well, the first point and the first way to solve the issue was to better understand what the Poisson bracket of something with a Lax matrix of the specific form that we introduced here could be written in terms of. And in fact, we just realized when looking at the Poisson brackets of the Lax matrix that you just needed to introduce three differential operators. Jz, J plus, and J minus. And here are the differential operators. Turns out that these differential operators realize an SL2 algebra. So you start seeing some SL2 structure coming in the game. And it turns out that if you now compute the Poisson bracket of the R matrix, the Lax matrix, because of the particular form of the Lax matrix, in fact, this Poisson bracket K123, previously described, has a very algebraic form. It's simply obtained by the action of the differential operators previously defined on the R matrix, tensorized by the Pauli matrices with the killing form in between. So you have a very natural explanation of what the Poisson bracket of L with the R matrix is. It's the action of derivative operators in SL2 on the R matrix. And this characterizes the Poisson, this dynamical part of the Poisson bracket, as coming not from the better known so-called abelian dynamical extension of Gervais-Neufelder, but coming from the so-called non-abelian dynamical extension, which was defined by Ping-Su in 2002 as a non-abelian extension of what had been done by Gervais-Neufelder. What this means is that instead of shifting along commuting vectors on the Lie algebra, you are shifting along the complete tangent space of the Lie algebra, SL2. Not completely, not the full, as we are going to see. In fact, it's a submanifold of the Lie algebra, but it remains something non-abelian. So we have this first nice result that the Poisson bracket of L with R are in fact non-abelian derivations along SL2. And then the second thing that one has to do is to decouple inside the R matrix the antisymmetric and the symmetric part. Why do we have to do this decoupling? Well, many studies about non-skew symmetric R matrices show that what you really have to think about when you're dealing with non-skew symmetric R matrices are some sort of reflection algebra with a set of two R matrices, the R matrix itself and the reflection matrix. And between this the R matrix and the reflection matrix, you have an extra action which is a which is a symmetric matrix, and that's the S component. So what you end up with is that you should in fact consider that the Young-Baxter equation described by Jean-Michel Maillet is a consequence of a set of Young-Baxter equations respectively obeyed by the antisymmetric part of the R matrix and obeyed by a combination of antisymmetric and symmetric part of the R matrix, which is actually better known as the adjoint Young-Baxter equation. So you have the fundamental Young-Baxter equation and the adjoint Young-Baxter equation. But in addition to this, you have the dynamical parts. So what turns out is that by trial and error, turns out that if you take the R matrix which Jean-Michel Maillet wrote, you take the antisymmetric part, you compute the antisymmetrizer here, the completely algebraic algebraic part of the Young-Baxter equation. If you try to complete it by some dynamical operators here, obtained by the action of this SL2 shifts, or SL2 derivative operators acting on the R matrix, in fact you don't get zero. You get this extra object, but this object is a very well-known object. It's the cubic invariant of the SL2 algebra. So, and you get the same object here when you look at the adjoint action. What you have to do to reconstruct the equation which Jean-Michel Maillet obtained is to take this equation, 3 copies of this equation with cyclic permutation of the indices, and add them, and you get exactly the Young-Baxter equation for the quantity A plus S equal R, which was written by Jean-Michel Maillet. You only have 2 derivative parts instead of 3 because the signs compete with one another to eliminate a number of contributions. And the omega just cancel out. 2 plus signs, 2 minus signs. But they were there from scratch. They were there if you were looking at the Young-Baxter equation for the antisymmetric part, and at the adjoint Young-Baxter equation for the symmetric part. So instead of having a Young-Baxter equation for the antisymmetric part, you have what's known as the modified Young-Baxter equation for the antisymmetric part, and the modified Young-Baxter equation also for the adjoint form. So to summarize what we have now, just a comment about the modified classical Young-Baxter equation, the one with this additional omega part. It's something that was also known from decades ago. It was mentioned by Semenov-Tianshansky in 1983, and if you look at how you deduce the form of the classical Young-Baxter equation from the Jacobi identity on the Poisson brackets, you realize that you have a perfect right to add such a piece to the complete algebraic object. And the modified Young-Baxter equation is a perfectly well acceptable condition for for the Jacobi identity of the Poisson bracket. There is no issue with that. Later on, Eitinghoff and Varchenko in 1998 and Ping in 2002, when he described the non-abelian dynamics, also indicated that there was one was perfectly okay with having this extra piece. In the fundamental Young-Baxter equation, as far as we know, there has been no proposal that the adjoint Young-Baxter equation, which is the one that pops up when you look at reflection algebra structures, that you were also legitimate in adding such a term. Well, it turns out that in complex sine-Gordon you have to add this term. That's what you get. To be more precise on how on what the operators that describe the Poisson bracket of the lax matrix with R really are, well, it turns out that these differential operators, the three operators, realize a linear representation of spin 1 SU2 when you act on three functions of this form, and the three functions are actually constrained by this following constraint. So what this tells you is that, in fact, the operators that you're dealing with, the operators that we have defined as the action of the lax matrix on R, are actually operators describing derivatives along a sphere and not derivatives in the full SL2 space. They are, in fact, living in the manifold. So we don't exactly have the situation with what described by Ping-Su in 2002, where he was describing the notion of non-abelian dynamical extension. The non-abelianity was the full algebra. Here it's not the full algebra, it's a quotient of the full algebra. It's not such a big surprise because the complex sine-Gordon equation, the complex sine-Gordon model was identified as a deformed Vesuminov-Witten model on SU2 cross / U1 by Ioannis Bakas in 1994. So the natural manifold, which you think about as the natural manifold on which a complex sine-Gordon equation should be defined is really an SU2 / U1 and not full SU2. So that makes sense that we have this sphere. And interestingly enough, now that we have all these nice things and coordinates, well, the antisymmetric and symmetric part of the R matrix now takes an extremely nice form. The antisymmetric part and symmetric part are essentially described, at least the dynamical part of these A and S, are described by a single element here, which takes a very canonical form. As a matter of fact, it is, in a sense, it's a canonical element. It's a scalar product of the spin 1/2 representation with this x plus x minus x0 vector. So it's a sort of canonical element. It's a very nice and very simple understanding of the form which was proposed by Maillet in 1986. Same thing for the S matrix. So we have identified that the general features of the Maillet proposal was that the R matrix consists of a pair of matrices A and S. So what you're expecting now, if you want, the next purpose now is to understand how to quantize the structure that we have found. Okay, we have a pair of matrices, antisymmetric and symmetric, that indicates that the natural quantized object must be a quantum reflection algebra a la Sklianin, or a slightly more complicated version a la Maillet-Fredel. Because of the dynamical properties of non-abelian type on the submanifold of SU2, which we have identified, clearly we have to discuss about a dynamical reflection algebra of non-abelian type. And because we have modified classical Yang-Baxter equation and not exactly classical Yang-Baxter equation, this suggests that we should think that at the quantum level, we should think about introducing a quasi-associator, because otherwise it's a little bit difficult to conceive where this extra piece would come from a classical limit. So that makes quite many problems. Plus an additional problem, which is we are talking about a reflection algebra with a dynamical extension. The problem is that reflection algebras have, as a matter of fact, already 3 identified dynamical extensions, non-equivalent, which can be summarized as follows. If you write a quantum dynamical reflection equation as follows here, with, I'm writing in the abelian case, so the shifts here are shifts along directions in an abelian Lie algebra. And the epsilons here characterize the relative signs of the shifts in the different components of the reflection algebra. It turns out that there are actually 3 different identified ways of writing a consistent deformation, consistent dynamical deformation of the reflection algebra. The first one is when this epsilon L and R have an opposite sign, and that's the original one, in a sense, the one which was defined by Baron, Peirce, and O'Brien when they discussed the integrability of boundary conditions for an SOS model, and which was later on described by Avan et al. As being, at the time they called it the boundary dynamical algebra, because it was the only dynamical algebra, dynamical extension of the boundary algebra at the time. Except that just 1 year later, Arutyunov, Chekhov, and Frolov described a completely different way of doing it, with one of the 2 epsilon being 0 and the other being 1. That's what we later called the semi-dynamical reflection algebra. And that's something that is characteristic, for instance, of the Calogero-Moser model or of the Roisener-Schneider model. So just one of the shifts is kept, the other one is set to 0. And it turns out that there is a third one. Epsilon R equal epsilon L. So here and here, opposite sign. This was one extension which Eric and I managed to build in 2012. Surprisingly enough, I mentioned that this extension here is characteristic of the Calogero-Moser model. As a matter of fact, it's characteristic of the first Poisson structure of the Calogero-Moser model, whereas this extension here is characteristic of the second Poisson structure of the Calogero-Moser model. It's quite well known that if you're dealing with dynamical R matrices, the first and second Poisson structure, in the sense of defined by Magritte for integrable models, have essentially nothing to do with one another, because the fact that you have dynamics completely transforms everything. Okay, I'm close. And the sign display that we have in our case, in complex sine-Gordon, suggests that in fact it's the third algebra that has to be considered. So, it's in fact, and the third algebra is one that we defined with Eric as being a twisted boundary algebra, the reason being that there is a way of constructing such dynamical algebras by taking a dynamical bulk algebra, taking the monodromy matrix and gluing the monodromy matrix onto a second monodromy matrix with a twist in between. If you don't add the twist, you get the found algebra. If you add the twist, you get this extra algebra. You change the sign of the shift. And that's why we call it twisted algebra. Obviously, so from the sign that we have here, the intuition is that it's the third algebra that will have to be considered. And we have a very big problem now, because the shift, I mean the dynamical structure that is described here, is not a dynamical structure along commuting directions. It's a dynamical structure along a sphere. And so how do you quantize? How do you manage to exponentiate these shifts? It's not completely clear. If you look at the paper by Ping, it's very formal. He adds some star operation, he adds some star exponential, and he manipulates very abstract objects. And if you ask the question, okay, how do I define a coproduct, a comodule, or trace structures? It's not completely obvious, because the whole structure defined by Ping is a very abstract one, with a form only defined by formal series. Not to mention the fact that we are dealing with reflection algebras, but that's something that we can probably work out correctly. And the final comment, since I'm running out of time, is how do we deal with the fact that we have to get as a limit a modified Yang-Baxter equation? Well, the way to deal with it is to think that probably what you're dealing with as a quantum algebra is not an associative algebra, but a quasi-associative algebra, and that you should probably look at quantum R matrices with further structure here, which is called the quantum Young-Baxter associator. This was already proposed by Drinfeld in the 90s. And indeed, if you look at the classical limit of that kind of stuff, and you assume that the classical limit of phi takes the following form, and you take the classical limit of this Young-Baxter equation that I just wrote, you're going to get the modified Young-Baxter equation. Moreover, there are some coproduct relations for the associator, and these coproduct relations are indeed obeyed at first leading order by the cubic invariant omega 1, 2, 3. So this indicates that we are probably on the right track. But then, question: how do you manipulate? How do you define a Lax matrix? How do you define a T matrix with an associator? It's obviously something that is going to intertwine everyone. So we are really, we know what we want to quantize. We have the full display of structure, but there are lots of difficulties, technical difficulties, and fundamental difficulties that will have to be addressed one after another. And this might be the reason why there are these anomalies, and the reason why there are these modifications, which Maillet and De Vega pointed out in '83. You have to really strongly and fundamentally modify the quantum structure compared to what you usually do when you quantize a classical integrable equation. And that's sort of the message I wanted to get through. So thank you very much for your attention. I'm done.